Okay, so here's a simple exercise. What is encoded 0? Let's see if we can solve this. And the answer is down there if we get stuck. And it's not defined, right? Because it depends on which order you concatenate. So if you start with this code and then concatenate that code, or if you start with this code and then concatenate this code. So there's actually 2 codes here. You just have to choose which one. So let's start with this code and then use this code. So if we start with that code, we first get 0, 0, 0. Now we have to use the dual code. So we need to expand out these guys in terms of plus minus and then expand each of them out. And so 0 is equal to 1/√2 times plus plus minus. Okay, we need some ket signs somewhere. Okay, and so 0, 0, 0 is equal to, okay, the combination of all of these. And so this is encoded as 1/8 times.
That's like all possible.
Yeah, this isn't hard. This isn't hard.
Minus,
Yeah, it's easy, right? Yeah, it's just plus 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 minus minus minus. That's the first 0 tensor 3. So this is 0 tensor 3. And so each of these zeros is equal to this. And each of these is encoded as plus 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 minus minus minus. So this is some 9-qubit state that represents the encoding of 0. Yeah. So is it clear what this actually, I mean, so you could expand this out again on the computational basis and you could argue that this still can correct X and Z errors. It's tricky because, I mean, there's 8 states in the superposition. It's just a mess to try to deal with it. So we don't, like, we never actually write out code words like this, probably. We just use stabilizer algebra. And it's a lot easier to see what's happening in stabilizer algebra. So let me explain just how that works. In this example, so this is stabilizer algebra, right? So we know X and Z, that's what these guys does. And so Z tensor Z just measures the parity of 2 qubits. Z is the parity of 1 qubit, even or odd, plus 1 or minus 1, plus 1 or minus 1. If you take Z tensor Z, that's the operator 1, minus 1, minus 1, 1 along the diagonal. And so you just get plus parity on the 0, 0, and 1, 1 state, and minus 1 parity on the 0, 1, and 1, 0 state. And so therefore, stabilizers for the 0, 0, 0, 1, 1, 1 code are these operations, ZZI and IZZ. Because this ZZI acts trivially on both these states, and IZZ acts trivially on both these states. And so therefore, any code word alpha 0, 0, 0 plus beta 1, 1, 1 is stabilized by both of these operators. And furthermore, these operators define a 2-dimensional space because there's 2 commuting Pauli operators. And the 2-dimensional space is exactly the span of these 2 basis states. Yes, and so instead of talking about the repetition code, instead we'll talk about the stabilizer code stabilized by these 2 parity checks or stabilizers. And then how do you act on them? So these are the stabilizers. The other thing you need to define a stabilizer code is the operations. So in this case, I need to define logical X and logical Z. And so a logical X is just how do you switch from logical 0 to logical 1? So if you want to go from 0, 0, 0 to 1, 1, 1, you just define X tensor X tensor X. And this works because X to XX commutes with ZZI and it commutes with IZZ. And so it takes a state that's a plus 1 state, it's plus 1 eigenstate of both of these, and it's the output after applying XXX is still a plus 1 eigenstate of both of these. So it takes the code space to the code space, and it actually operates non-trivially inside that code space like this. Logical Z is, for example, ZII, because if you just measure one of the qubits in the Z basis, that tells you the logical Z state, the computational basis state. So either computational 0 or computational 1. It tells you the whole state. And of course, it doesn't matter which of these. So here, ZII, it commutes with both of these, and it anti-commutes with the logical X. So logical Z has to anti-commute with logical X because X anti-commutes with Z. But this is not the only choice. So for example, if I multiply this logical operator by zi to get zi, you could use that just as well. Or you can multiply by both of these and you get iiz, and that's fine too, it's equivalent. So logical z is any of the three physical z operators. Okay, and so that's what I'm doing here then, is I'm compiling, so what I've done here is I've taken the repetition code. So the repetition code is zzi, izz, so this is the 3-qubit repetition code 3 different times. And so what I mean is, this is a 9-qubit stabilizer. So these guys are the identity on the last 6 and only working on the first 3 qubits. These guys are only working on the middle 3 qubits, and these guys are only working on the last 3 qubits. And so I have 3 copies of the repetition code. And now what we did again up here. So 3 copies of repetition code. Okay, so next I'm going to go into the dual repetition code. So the dual repetition code, again, it's the same code, except the stabilizers are xi and ixx. So now we want to use them at the logical level. And so we only need logical x on this block, logical x on this block, and logical I on this block. Logical x is xxx. And so you just get xxx, xxx, I, that's this one, and I, xxx. So that logical identity, logical x, logical x. So this is the dual repetition code at the encoded level for the first repetition code. So here, if you count this, I have 1, 2, 3, 4, 5, 6, 7, 8. I have 8 different Pauli operators. They're independent of each other. It's sort of obvious, I guess. You can't multiply them to get the identity. They're independent of each other, and they commute with each other because these commute, these commute, these commute. These are logical operators, so they commute with these. Everything commutes. And so I have 8 independent commuting things. On 9 qubits, that means there's still 2 dimensions. There's still one logical qubit encoded. So remember, every stabilizer reduces the dimension of the +1 eigenspace by a factor of 2. So if I have 8 of them, and I started with 9 dimensions. If I start with 2 of the 9 dimensions of freedom, after 8 stabilizers, I still have 2 to the 9 minus 8. I have one qubit left. And so, right, okay. So these are the